Okay, so it's been a while. So last week we had an exam. But before that exam and the studying for it and the examples of regular pumping lemmas, we were in the process of talking about context-free pumping lemmas. So let's recap that because it's been a hot minute since we talked about it. All right, so differences between regular pumping lemma and context-free pumping lemma is now instead of being able to break the string down into X, Y, Z, we're breaking it into U, V, W, X, Y. No. No, it's V, W, X, Y, Z. No, it was a missing something somewhere. Anyway, the middle of it is VXY. That's right, there's no W. W is, of course. So VXY, it'll be a UVXYZ. There we go. So the idea behind this center section is that we have some recursion. We need some way to be able to produce to get from a non-terminal back to that same non-terminal. And just like the idea was in regular languages, that any string that is longer than the number of states in the DFA is going to have some loop in it. The idea is any string longer than the number of productions in a grammar is going to have some number of repeated productions as long as we have some rule associated with the number of terminals that a non-terminal can go to. So we have something like GNF, Greibach normal form, that allows us to only get a single terminal out of it. So we can just rewrite any grammar as any grammar that can generate a single terminal in a production at most. And then we know that we will be having recursion for any string that is longer than the number of productions in the grammar. So let's say we have 5 productions in the grammar, we have a string that's of length 6. Now we know that at most, each non-terminal can produce a single terminal and then some more non-terminals. So in order to be able to terminate that grammar, then we have to have seen at least 2 of the same non-terminal. Which means that there is some recursion. We have a non-terminal that can, via some sequence of productions, produce itself. So A produces B, produces C, produces A, something like that, where we have a recursive process. And this is also the intuition behind why any problem that can be solved with a loop can be solved with recursion and vice versa, is that we can actually map them onto each other like this. You would just write a program that emulates the expansion of non-terminals and productions in a grammar, and that loop would be emulating the recursion that's taking place. Similarly, you could take a loop, write them in terms of a grammar with non-terminals, and now you would have a recursion that emulates that loop. All right, so we determined that this was the recursive step, this concept of we have this non-terminal. This non-terminal is going to be producing something on either side of that as it produces something before the recursion, some substring before and some substring after. We call that V and Y. So every time we go from A to A recursively, we will produce this before the recursion and after the recursion as the terminals that were produced in that process. Does that make sense? Do people have any questions about that idea? I liked the visual that we had for it. I'll just pop right over to the visual so that we can see it for a second. As we go from A to A, somehow, via some sequence of productions, we're going to be producing parts of the string that we're going to label V and Y. And then we have the ability to do that an arbitrary number of times. And that produces an infinite number of strings. We're going to see that we do this once, and this once, and this that arbitrary number of times. So we'll get U, V, X, Y, Z, U, V, V, X, Y, Y, Z, U, V, 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 X, Y, 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 Z, etc. There's no limit to the number of times we can do that. We also have the associated rules for this. We know that the length of Vxy has to be less than or equal to m, whereas before m stood for the number of states in the DFA. Now we have the number of productions in the grammar. We need the string that we pick that needs to be of size greater than or equal to m. So the string we pick needs to be longer than the number of productions in the grammar to make sure that that recursion is present in that string. We need that to be the case. It's very similar to the regular rule that the length of W had to be greater than or equal to the number of states in the DFA because we needed to have iterated that loop at least once. So once those are true, we can decompose it into UVXYZ, where we talked about VXY. That's an iteration of the recursion. U is the front part of the string that we generate when we get to the first recursion, going from the start state of the grammar to the first instance of that recursion. Z is what's generated going, it's in the back part of the string from that recursion. And then X was going from the last recursive procedure to the termination of the grammar. Questions on any of those ideas before we get some examples? So this visual helps a lot. We start at the start state of the grammar. As we get to our first instance of this non-terminal A that's going to be recursive, we are going to generate some front of the string U and some back of the string Z. That's just the process of getting from S to A. So maybe we have some production that looks like this. Let's say we have there's nothing else that we can do with S. In order to get this A, we produce this A at the front and this B at the back. So this A represents the U, this B represents the Z, and then we're going to identify this recursive process of what happens from the first A to the next A. So maybe we have a rule, A arrow, I don't know, maybe we have a B, capital B, C, and then we have B arrow, C, capital A, A. And now we see where that recursion is embedded. Where we now, I guess, need some way to terminate this string. So let's say this B can be empty. We want it to be something else. Let's say CA. Okay, there doesn't have to be something in between. So we need to go from this A to generate some other A. So to do this, to get from A back to A, what do we have to do? We need to generate a B so this recursive procedure going from A to A generates the substring B, C, we have our marker in the middle of it, followed by A, C. Does that make sense? How we're generating that portion of that string between one definition of A to the next. So we had the A and the B up front that we did once getting to this A, but now when we have this A in the middle of this again, we could do this an arbitrary number of times, right? We can recurse from A to A to A to A to A as many times as we wanted to. And each time we would produce this substring at the front and this substring in the rear. So we're going to call this substring here, we're going to call this V, we're going to call this Y. What do we see? We should be doing a depth first search. Because the B is all going to go in between this B and this C. So all of this needs to go between that. So the B does have to come first. It's a good point. So now how do we go from the A to termination? Well, to get to termination, this is the only way this grammar can terminate right here. So to get from this to that, we have to get to B and then to that. So we're going to, at the very end, generate our same B, B, C, and then the B can become CA. So now, this whole string here, between this B and the Y, this becomes your X. Because this is what's needed to go from the last iteration of the recursion to termination. They're the characters that need to be put in the middle there to terminate the grammar. So that's the intuition behind what each of these letters mean. The U and the Z happen once, getting from the start to the first iteration of the recursion. The V and the Y happen an arbitrary number of times for each time we do the recursion from A to A. And then the X are all of the symbols that we need to go from the last recursion to termination. So now we kind of have a way of defining some strings in this language. First of all, do we need to include a U and a Z? Is it possible those are empty? What makes people say no? We could, but we could also define the recursion interestingly. Like, what if we had a first grammar rule that was like this? Yeah, for this particular grammar, the answer would be no. There's no way to get to A without creating symbols. But in general, yes, U and or Z can be empty. You don't have to think of them as containing something, but you could have some kind of recursion in this that does not actually create any terminals. If you don't create any terminals, then U and Z and or Z would be empty. Same with any of these, they can all be empty, except that we know that the grammar must have some recursion in it. And in order to be an infinite language, and for us, our string to be longer than the number of productions in the grammar, the concept of bxy needs to be of length. Sorry, it was vy, needs to be of length 1 or greater. So we do need to have a recursion that can generate at least one terminal in the grammar. Any other part of this is pretty open. Questions on the logic of at least the terminology that we're using in terms of the letters and what they represent? Right. We'll move on to some examples. I first want to talk again about the pumping lemma game because I find this to be an intuitive way to think about this process of deriving this proof. So again, the game is very similar to, this is kind of why I don't like it, but instantiating this value of m, because one of the players is going to pick a value of m. And to make it a game, you have to give players choices. And again, when you write this as a proof, you want to make sure that that stays a variable to show that no matter what player one does, player two always wins. If you can generate that proof that in this game, player two always wins, that's your proof. So again, player one picks m, it's exactly the same game. So player one instantiates m. Says, I believe in the regular language version, a DFA with this many states exists. In this case, they're going to be saying a grammar with this many productions exists. Player two picks the string, length at least m, whatever m they picked, then player one gets to choose the decomposition of vxy. They do have to adhere that the length of vxy has to be less than or equal to m. Once player one does this, player two will choose the value of I such that uv to the I, xy to the iz is not an L. If player two can do this, they have won the game. If player two cannot do this, then player one has defeated them. The idea is that if this language is not context-free, then player two has all of the ability to win this game. If player two plays optimally, they cannot lose the game. And that's what your proof focus should be on, is showing that in general, regardless of what player one does, player two can win the game. If you can do that, then you've shown this language is not context-free. Questions on phrasing this as a game? World's most boring game, but a game nonetheless. All right, for some examples. Show that the language A to the N, B to the N, C to the N is not context-free. So as usual, we want to pick a good string to start, because in the game, player one picks M, but we have to show that no matter what player one would pick for M, we have a counterexample. So where we're going to start in general is picking the string. Player one picks M, it doesn't matter what they pick, we need to show for all M, regardless of what you pick, there is no grammar with any number of productions that we can generate for this language that adheres to the context-free grammar rules. Let's start with a little bit of intuition. Why isn't this language context-free? So if it were context-free with an infinite amount of memory and a stack of infinite size, we should be able to recognize this language. Why is that difficult with a stack? Kind of algorithmically, how did you proceed with this? We have some string that we're going to read. Maybe it starts with an A. And we have a stack, an infinitely sized stack. We want to see if this string adheres to A to the N, B to the N, C to the N. We don't know when we start what the value of N is. We have to read A's until we know what the value of N is. But let's say this string is something like, I don't know, A, B, 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 C, C, C. So that would be in the language. How would we proceed? We read some A's. We put some A's on the stack to show that we read these A's. If we wanted to recognize A to the N, B to the N, we then map the B's to the A's. So when we saw Bs, we would pop off the number of Bs that are on the stack. So we would see 3 Bs, pop off 3 As, and have an empty stack again, so we could accept. But now we move on to the Cs, and we see now we need there to be the same number of Cs as there were As and Bs before that. But now we have no representation of how many As and Bs that we saw. Okay. Well, maybe we could add 3 As and then add 3 Bs. And now we need some way to say, okay, when we see the 3 Cs, we need to map them to the prior As and Bs that we saw. First of all, do we know that there were the same number of As and Bs in here? Not necessarily, yeah. What's your idea?
You can pop more than one character, right?
Yes.
So what do you do, 0?
This would be trivial if we had 2 stacks. Right? We had 2 stacks, we put the A's on the first stack. We could pop off the A's and on the B's to determine if this stack is empty, then this stack has the same number of B's that there were A's. So now we don't need to worry about that. So we can just put the A's back on for each of the B's that we just did, and then we would map the C's by popping the A and the B. But the issue is, then A to the n, B to the n, C to the n, what happens if we do a D to the n? Now we need 3 stacks. E to the n, now we need 4 stacks. Is there a way with a single stack to do it? Taking that intuition with us is going to help us to be able to pick a good string. So if we were asked to show this, what do we think is a reasonable string to run with? Not a ton of options here, but. What should we pick? We know that our constraints are the string needs to be longer than m. We haven't defined an m yet, so we need to write the string in terms of m. But we could pick something like, I guess I can just reveal it. A to the m, B to the m, C to the m. Right? Whatever player 1 picks for m, that determines what this string is going to be. We have now a formula for creating a string based on whatever player 1 happens to say. That's what's important for this and bringing it back to the game. The reason this is good is player 1 has to pick a VXY. Remember the constraint on this is that VXY is less, the length of that is less than or equal to m. So we can pick all A's, all B's, all C's, a mix of A's and B's, or a mix of B's and C's. That's the only window of length m over this entire string. We can't choose A's and it's anything that contains both A's and C's. Does that make sense? There are m B's in the middle. If our sliding window is of length m, we can't have both A's and C's. So this creates 5 cases. All A's, all B's, all C's, some A's, some B's, some B's, some C's. So that's how we're going to proceed, is by looking at this in terms of those 5 cases. We need to show that that any of these 5 cases produces something that is wrong. Once we pump this VXY, so this VY, regardless of the pick, any I greater than 1 produces some string not in L. The all A's case is really easy to visualize, for instance. So let's say again, we have this string A, B, C. So we're running with some m equals 3. And again, do not include this as part of the proof. This is only for visualization purposes. We need to show it for any m, but I think it helps to have an example in front of us. So we are arguing that Bxy is sum all a's component. Any of these cases would be considered in Bxy is all a's. If this is the case, let's set I equal to 2. So we know Vy contains at least one A because the rule was the length of Vy has to be greater than or equal to 1. When you take this into account, the Vy has to be at least a single A. It could be more than one A, but the point will be served with a single A. When we do this, we end up with A to the m plus the length of Vy, B to the m, C to the m. And since we know that the length of Vy has to be greater than or equal to 1, when we pump this Vy an extra time, we get the length of Vy more A's at the start of this strip, which is going to be at least one of them. So in the best case, we have A to the m plus 1, B to the m, C to the m, which is not in the language, right? That's an example of a string that should not be in the language. But because once we pump Vy an extra time, now we end up with more A's than B's or C's. Not in the language. Great. That works for this case of Vy coming from all A's. This same argument works for the B's and the C's. The only thing that you would need to change is that in the B's case, you would have A to the m, B to the m plus the length of Vy, C to the m, and in the C's case, you would have A to the m, B to the m, C to the m plus the length of Vy. These will be your proofs for these first 3 cases. Is you end up with either more A's than B's and C's, more B's than A's and C's, or more C's than A's and B's. The next 2 are a little bit trickier. So we need to show this for all 5 of these cases, because we need to show that for any possible breakdown of X, Y, Z, there's no good breakdown. What if we choose some A's and some B's? The overlap between this now can't be longer than m. In this case, m was 3, but now we could choose something like, it needs to contain A's and B's. So we could do an A and a B, 2 A's and a B, or an A and 2 B's. Can't be longer than m in this case. But those are all valid choices of Bxy. If that's the case, what could we do to pump this to show an example of a string that's not in the language? Is there an I that makes sense here? Yeah, literally any I would work here. Because let's pick I equals 2. The reasoning that you're going to have to go through is that regardless of how this is broken down, it has some A's and some B's. If you pump this one additional time, then we break the structure of this string, because we're going to be producing extra A's and B's. We're going to have our m A's, A to the m, and then by the time we're done with at least one B will have passed, we're going to see some A again somewhere along here once we repeat this. if we have AB, then we would end up with the string, let's actually draw it out for 3 different cases. I think that will be easiest. Let's go right here. We would have A, B, A, B, 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 C, C, C. Not only do we have more A's and B's than C's now, but we've also broken the structure of the string by pumping an extra AB. If BY were this entire thing. But do note that B and Y could also be where we have the B here, the Y here, and the X is empty. So this could produce the string A, B, 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 C, C, C. But regardless of what you do, when you pick at least an A and a B, and you set this I equal to something that is above 1, you end up with more A's and B's than you have C's. So you could take this in 2 different directions. One is the form of the string, but the easier way to do this one is going to be this way, saying how many A's and B's are you adding? So I would argue that for A's and B's, you would have the case where you have A to the M plus. And how would I want to write this? Because we know that this AB can either come from B or Y, but we don't know how many A's there are going to be in that. We know it's at least 1 though. So you'd have to define mathematically some way to tie that idea together if you wanted to formalize this. But the idea is there's going to be at least 1 A, 1 or more A's. How do I want to write that? Plus 1 or more. B to the M plus at least 1, C to the M, which breaks the rules of how this is going to need to work to be in our language. And if you pick B's and C's, you'll end up with something that looks like A to the M, B to the M plus at least 1 character, C to the M plus at least 1 character. So regardless of any of these forms, none of these forms are in that language. Which shows that there is no valid grammar that we can make for this. Because we picked a string that is longer than the number of productions. If we were to scale the number of productions, we would be scaling the length of this string. If we scale the length of this string, we can always break it in one way or another by iterating where that recursion has to be. The recursion could be in any of these 5 places, and regardless of where that recursion is, as soon as you go through that recursion once, you've produced something that's not in the language. Because that's the case for all 5 of these cases, then we can conclude that this language is not context-free. So if we wanted to use some kind of predicate logic to describe this, in case maybe that's something that you've seen before, we need to break this down into all of these cases. So kind of think of this as for all of these cases, there exists some I such that for all of these cases, like there exists, when you do this, we have a string that is not in the language. So this cannot do that. So you would have a, for all, there exists, example. That tells you that you're going to need 5 of these things in this case. So there are 5 cases, there exists an I, 5 times 1 is 5 examples here. Any questions on this example? I know this is a lot. Maybe show of thumbs for how clear this concept is. Are you familiar with, can you logic why these exact examples and this breakdown lead to this proof? That's probably what I'm the most curious about. If this intuitively makes sense, give me a thumbs up. If this intuitively is somewhere in the middle,
On the homework, would we have to write out all cases?
yes, you would need to show that. But you could break this down further. If you wanted to show all of the logic between, you could say this is similar to this because more bees. I'm not requiring an absolute formal math proof at this stage, but I would need all of the logic to be there for me to know that you understand. All of these cases has an associated breakdown, and you need to communicate that very clearly. It can't just be, an image with another image next to it. Don't make me read your mind. Walk me through it logically. If it's logically there, I will accept it. It doesn't have to be written as an exact formal math proof. I think it's better if you can formulate it that way, because the practice that you would get from that would help you to be able to read future math proofs, because we've all seen math proofs. They don't walk you through it logically. It's just, here it is. And that's not really useful for anybody, I find. But yeah, if you logically walk me through it, this is not a complete math proof. But this is the logic that says these are the only 5 ways you can break it down. Here's what the resulting string would look like if you pumped in an extra time. These are all obviously not in that language. Because they're all logically not in that language, then I can conclude that this language is not context-free. Because there is no way that a grammar with any number of productions could exist. Good enough. Any other questions? Questions remotely? How are we doing? Time for another example. Probably our last example of the day, but we will see. All right, we have another language. WW. First of all, intuitively, what does WW mean?
The same string repeating?
Yeah, we can break the string in half, and the first half and second half are identical strings. But of course, going into it, we don't know how long that string is going to be. So we don't know where that midpoint is going to be. We're going to need some way of determining where that midpoint is.
They have to be identical.
They do have to be identical according to WW. So you could have a string ABB, ABB that would adhere to this language, because we have W equals ABB. So this string would be in that language. Does there exist a W such that the first half of the string is W and the second half of the string is W? Divided right in between. Now you could come up with something that's really nasty, like something like this. This is not in WW, even though it starts with the same substring and ends with the same substring. There's overlap between those, so it does not count. So what procedure could you use? Could you write an algorithm to recognize a WW with a single pass from left to right with a stack? We're already saying that show this is not context free, so that's not going to be possible. It'd be much nicer if we had a queue. Because we found that WWR was possible. So WW would be possible if we had a Q and not a stack. So given this, let's start thinking about the intuition of how we might pick a string that would show that this is not the case. So what is a good string to pick to move into a proof to show that this is not context-free? This one's a little bit trickier. Try to think of what this string should be. Any ideas? We have to have M in there somewhere.
We just do it now,
Do what?
ABB.
We have to have an M in there somewhere that tells us that it scales based on the potential size of the grammar. If there is a grammar for this, then it should be able to produce any string that adheres to this constraint. So we want to pick a string that's going to make this process as easy as possible. To think of all possible breakdowns into UVXYZ, breaking it into cases and showing that regardless of those cases, we can iterate this, pick an I basically, that shows that the resulting string is not in this language. Any ideas? This is the hardest intuition to get in these problems, I think. It's picking a good string. One suggestion is AB to the M, AB to the M. That's intriguing. So AB to the M, AB to the M. This would work. So, well, I don't know about for the proof, but this is in the language, right? We have a W and a W. Regardless of the size of M, this will always adhere to that language. If we wanted to run with this, we would know that within M characters somewhere, we would have VXY. What could all of the forms of that be? We would have starts with an A, ends with an A, starts with an A, ends with a B, starts with a B, ends with an A, starts with a B, ends with a B. Those would be the four cases that I could come up with for all possible breakdowns of VXY. Such that we have a sliding window of M across this. Oh, sorry, sliding window of up to M. If it were exactly M, then we wouldn't have the ends in A's and ends in B's, because that's going to be an odd length string. But since it can be up to that, all four of these cases are possible. This is going to be really tricky to prove, and this is where you should start to abandon the string as an idea. Because if you repeat A to B like this, you're going to end up with something that's in the language. If you take out A to B, you're going to end up with something that's still in the language. Let's give you an example of instantiating this. So we would have, let's pick 3 again. So we have A, B, A, B, A, B, A, B, A, B, A, B. So here is W and W. somewhere along this sliding window of length up to M, where M is now 3 characters, so we can have up to 3 characters of BXY. So we can see that we can generate anywhere something that starts with an A and ends with an A, either just by picking an A or picking an ABA. We could start with an A and end with a B if we picked AB. We could start with a B, end with an A if we picked any BA. We could start with a B and end with a B if we picked just B or BAB. So these are our 4 general cases. The issue is for this one and this one, it's going to be impossible to show this. Let's say we pick AB. If we pump this an arbitrary number of times, we're going to be producing more and more ABs. And as long as we have an even number of them, we end up with a string that's in the language. If we take it out, we wouldn't. But if this scaled to be any longer, then it would be possible to make an ABAB that if we took that out, would adhere to it. So we would not be able to prove this one way or another in these 2 cases. So this was a really good idea because we picked a string that's in the language. We were able to break it down and we were able to logically think about how this would work. But there are going to be 2 cases that's going to make this impossible when we scale it. So really good idea. And in fact, the string that we're going to run with is kind of like this. Any guesses for what that string might be? Does it, first of all, does it make sense why this would not work? I made a mistake by picking M equals 3. If I pick M equals 4, then it's easier to show why this would not work. Because now I can pick ABAB, and if I take out an ABAB anywhere from this, we end up, let's say that we carve that out. We end up with an ABABAB, ABABAB that works as a WW.
Like A to the M B or like B to the M A.
Yeah, that's along the right track of thinking here. So we're gonna run with A to the M, B to the M, A to the M, B to the M. First of all, does it adhere to WW? Why is this a good string? Why is this a better string than AB to the M, AB to the M? Which was a good idea. I actually really appreciate having that example to work off of to show why that's a close but not quite correct pick. If we're going to have a sliding window of up to length M in this string, what can we now say about VXY? There are only 3 cases now. We have all A's, all B's, or a mix of A's and B's. So only 3 cases that we need to show. First of all, if we had all A's, what would our counter argument be? So our VXY is all A's. That means that the length of Vy is greater than or equal to 1. We know that it's a preliminary. So we're going to be, if we take an I greater than 1, we're going to be adding A's to this first section. Or if we take I equals 0, we're going to be removing A's. Can anything where we add or remove just A's to this string produce a string that's in the language? No, and we have 2 points of attack. The number of A's here is different from the number of B's here. Or the number of A's here is different from the number of A's here, after we add or subtract at least 1 A from this section. 2 ways to show that this is not in the language. Now, note that this doesn't have to be here. This argument would also need to work if you picked all A's here. So you would just say, pick the B's that are associated with those, or pick the other set of A's. Regardless of that, you would have some point of attack that says we need these to be equal to each other, and they are not. Once we pump the string. Same argument works for all B's. Pick the associated A's or pick the other set of B's. Regardless, you don't have the same number of them as soon as you add at least one or subtract at least one. The harder part is in the middle where we have potentially some A's and some B's. And this is where we're going to have to show that either we're adding some A's and B's here, therefore they're not going to be the same as here, or it's going to break the sequence of A's and B's that need to be associated with the string. But we are unfortunately out of time, so we're going to have to pick this up again tomorrow. We have a couple more examples coming, but I think that's good. We also have a homework due on Wednesday. So let me know if I can be useful for that. I have office hours starting now, if I can help you with any problems. See you tomorrow.
You know what, the week of